Dua Lipa right now. This one's Hallucinates on 987.
According to the World Health Organization, road injuries pose a significant global health issue. In Singapore, 108 people died in traffic accidents last year, which is an increase from 2021. As such, it is imperative that we address the issue of road safety.
To start off, we first need to identify the problem statement. How can we utilize technological advancements to improve the safety of our roads? To solve this problem, we need to examine the underlying factors that contribute to road accidents. Secondly, explore how technology can mitigate these factors. To answer these questions and factors, we will be collecting data and answering them using meaningful statistics. Next, central limit theorem. For the data collected, we have ensured that the size of the datasets are more than 30. This allows us to estimate that each variable follows a close to normal distribution. This allows us to apply hypothesis testing as well and confidence interval analysis in a fairly general condition. Next, we also assume that our points are independent and identically distributed. When we mention identically distributed, sample points reflect the population data since each accident conforms to the population distribution. As for independence, the sample points are statistically uncorrelated as the incidence of one traffic accident does not influence the occurrence of another.
Before we can implement solutions to make our roads safer, we need to determine the root causes of why motor accidents occur. After conducting our research, we have come up with the following regression model. We chose the dependent variable y as TOFAT, which measures the total fatalities per 100,000 people. We also have 4 other independent variables, which are firstly, speed, which measures the speed limit of the car at the time of the accident. Secondly, alertness, which indicates whether the driver was alert at the time of the accident. Thirdly, blind, which indicates whether the accident originated from the driver's blind spot. And lastly, male, which indicates whether the driver is male or female. From the results, we identified that alertness and the presence of blind spots were strongly correlated to total fatalities with an absolute correlation coefficient of 0.521 and 0.525 respectively. However, we recognize that correlation does not equate to causation and only measures association. Furthermore, we are unable to determine the quantitative impact of these factors on total fatalities. Thus, we need to incorporate the linear regression model to further prove that alertness and the presence of blind spots are the main factors that cause car accidents.
Now that we have decided upon which variables we want to use, we want to derive the relationship between the independent variables with the dependent variable. We can do this by coming up with a linear regression model. First things first, we want to find out the distribution of our dependent variable. Currently, TOFAT has a skewness of more than 1, and as seen from the histogram on the right, it is very right skewed. So to make our dependent variable more normally distributed instead, we can log our total fatalities variable, and we now see that once we run a skewness command on R, it has a skewness indicator of 0.04, which is much closer to 0. And as seen from the histogram on the right, it resembles a more normal distribution now. So when we log our linear regression, we have to be careful that we don't log every single variable. The reason is because alert, blind, as well as the male variables are categorical variables. They are made up of zeros and ones, and it doesn't make sense to log these variables. Moreover, we will get an error if we attempt to do so. So we'll be using the ordinary least square regression to find the coefficients of our linear regression model. And because we have used the ordinary least square regression, according to the Gauss-Markov theorem, coefficients that we have found are blue, or the best linear unbiased estimators. However, just because the coefficients we have found are blue, it does not mean our regression model is useful. We also need to perform a t-test to find the p-values. The p-values, or the statistical significance of our coefficients, can be seen by the number of stars within the yellow box. We see that the variables of log speed, alert, as well as blind all have 3 stars, which means they have a p-value of less than 0.001 and are thus statistically significant.
Now that we've known that our model is useful, let's interpret the coefficient of the independent variables. Firstly, with every 1% increase in speed, there is a 0.33% increase in total fatalities, with everything else being equal. Next, when the driver is alert, there is a 28.55% decrease in total fatalities, with everything else being equal. Next, when the driver fails to check for his blind spots, there is a 24.44% increase in total fatalities, with everything else being equal. Lastly, the coefficient for male means that there is a 0.29% increase in total fatalities when driver is a male, with everything else being equal. The respective p-values will indicate whether the null hypothesis of the coefficient values equals to 0 is to be rejected. Since the p-values for speed, alert, and blind are less than 0.01, we can conclude that these coefficient values are statistically significant at the 1% significance level, and we will reject the null hypothesis. Whereas for male, the coefficient value is statistically insignificant as the p-value is above 0.1. Hence, we will not reject the null hypothesis. Overall, this will mean that the speed, alertness of driver, and blind spots are key contributing factors to road traffic accidents. Now, let's take a look at how we can use technology to reduce road traffic accidents. Firstly, the blind spot detection system is a technology which will warn the drivers visually and audibly when the driver tries to switch lane when other vehicles are approaching or within the vehicle's blind spot. Next, driver's monitoring system is another technology which uses AI and computer vision to monitor the alertness of drivers. When drivers are distracted or falling asleep, it will send out alerts to remind them to stay focused on the road.
Now, we will run another linear regression model to quantify the effectiveness of our solutions in improving road safety. In order to assess road safety, we will be using the same dependent variable of total fatalities per 100,000 population. As for our independent variables, they will be the technologies we implemented, namely the blind spot detection system and the driver monitoring system. Do take note that both of them are categorical variables in this model. Before we proceed with our regression model, we should check the skewness of our dependent variable to determine if we should perform a log transformation. Using the skewness command, we found that it had a skewness value of 1.066, which suggests that the data is highly skewed, and thus, we decided to perform log transformation, which helped us to get a relatively normal distribution with a skewness value of negative 0.028. Our linear regression model can then be represented by the following. As we can see from the regression model, the coefficients of both solutions are negative 0.36130 and negative 0.29178 respectively. How we can interpret the coefficients would be that for beta 1, there will be an average of 36.13% decrease in road fatalities when BSDS is implemented, with everything else being equal. As for beta 2, we can interpret it as there will be an average of 29.178% decrease in road fatalities when DMS is implemented, with everything else being equal.
Moving on to the respective p-values, we can observe that both have a value of 2 times 10 to the power of negative 16, which is less than 0.01. This suggests that there is strong evidence to reject the null hypothesis of beta 1 and beta 2 being equal to 0 at a 1% significance level. Thus, we can conclude that the coefficients are statistically significant at a 1% significance level. Therefore, we can conclude that both BSDS and DMS do have a substantial impact on the road safety in Singapore by reducing the total number of deaths which would have otherwise occurred without its existence.
Now, let's take a look at how the scenario at the start would have played out with our technologies in place.
The alerts reminded the driver to stop using his phone and to stay focused while driving, thus preventing road tragedies from occurring.
In this video, we have identified some of the root causes of road traffic accidents. Subsequently, we came up with 2 technological strategies that will hopefully reduce the likelihood of accidents. Through statistical analysis, we have proven the efficacy of these strategies. As such, we hope to protect lives by preventing such road tragedies. This is the end of our project. Thank you, bro!